Welcome to the second video on the solutions to the activities in the Part A lecture notebook of Module 4. So for the second activity, you are asked to implement a bisection variant. The same three notes as the previous activity also apply here, and I'm asking you to create a function, compute false, that performs the false position method. You make sure that it tests that the conditions are appropriate for running this algorithm. While not required, it is highly suggested that you also put in a useful docstring and doctest for this function. You can do this by copying and pasting the compute bisection function below, editing its name, and editing the single line of code involved with computing C. That will just at least do the first part, computing the false. It won't mean that you're adding the docstring and doctest for it, which I really recommend you do. You should definitely edit, though, some of the code comments in the docstring that are in there, because otherwise they're not relevant, and that part of the code is then wrong. Comments and docstrings are part of the code, so if you copy and paste a piece of code and edit it, and you don't change corresponding code comments or docstrings, you've done something incorrect. So we'll go ahead and do that. Now, I say you can do this by copying and pasting compute bisection below, editing its name, and editing the single line of code, and then editing some other stuff. So let's go ahead and grab the compute bisection function, which is near the top of this lecture notebook. So it's right here. So we'll grab this. We're going to copy it, the code contents there, and then we're going to put them here. Now, this is supposed to be compute false at this point. Certainly, this is a simple function, applies up to n iterations of the false position algorithm, right? That's what we're doing here. We're doing the false position method or false position algorithm. And then let's check to see that we work with the false position algorithm. Let's just change some of these code. Everywhere we see bisection, we should say false position algorithm. And we're not going to compute a midpoint anymore. So the false position, as was described above, is based on linear interpolation. So I provide a wiki link here that you can click on. I'll just go to the page here, and I went down to where the method is inside the wiki page. So you should bring you here, and you can click on the false position method. It's all illustrated here. I think I talked about this in the lecture notebook as well. You pick an A and a B, you're bracketing a root, but instead of taking the midpoint, you create a line that connects the 2 points, A, f of A, and B, f of B. And then it says, where does that line intersect the x-axis? What's a root for that line? And then you use that instead of the midpoint as the approximate root. And what it does is it says, okay, well, look, here's the line. Here's an equation for a line in point slope form that connects the 2 points, the A, f of A, and B, f of B at the kth iteration. And then to find where it's equal to 0, you basically are saying, okay, well, set this equation equal to 0 and solve for y. That's all you're doing. So they move basically all of this over to the one side of the equation, and then you set it equal to 0, solve for y, and call that y the c value. That's what you do. In the end, you can use one of these two forms. You can use this form or this form. I'm just going to go ahead and code up this form. Oop, I should maybe have zoomed in. This form right here, the a f of b minus b f of a divided by f of b minus f of a. Remember, we're updating A and B each time, so we don't have any of these subscripts. So, we're going to compute the root of the line connecting A, f of A, and B, f of B. Because it's not a midpoint anymore, this is the appropriate thing. And this is the one line of code that we really have to change in order to get the false position to work. We need to code this up. So A times f of B minus B times f of A divided by f of B minus f of A. So let's do that right now. So the numerator is A times, or let me make sure I get that right again. A times f of B, A times f of B, minus B times f of A, right? B times f of A, and then divided by f of B minus f of A. So then we'll divide by the denominator f of B minus f of A. And just pay attention to the parentheses are needed here in order to group these operations. That whole numerator divided by that whole denominator. We can have these same things here in terms of these checks and checking if the iterations are too small. Now, we do need to make sure that the conditions are appropriate for running this algorithm. In the one of the things that can happen here is you could potentially divide by 0, right? If f of b and f of a ever become the same thing. That actually won't necessarily happen here. As long as these are different signs, and we're testing that here as well, they can never be equal to each other. So we don't necessarily have to check anything here. Basically, the same conditions that hold for bisection hold for compute false. So this is checking this. But now again, notice when we're checking this, we need to say the false position algorithm. The false position algorithm. And I'm just using a little abbreviation there. All right, let's just see if we have anything else where we say bisection. Nope, that's it. So this is it. That's all you really had to do to create the compute false algorithm. You had to change the name. And we had to, change some code comments, a docstring a little bit, and this one line of code. That is, I believe, it. So that should create that function. And now all you're asked to do are to compute the false position algorithm on some Lambda functions with and without widgets. So if you recall at the start of this notebook, I was showing some places where I was computing bisection. Right? I was showing some, things involving bisection, and I was also showing it with widgets. I'm just asking you to do that again here. So I could let's go ahead and copy. Let's create we could we'll do this. I mean, maybe I'll do this one. I'll just go ahead and, I like this one. I'll do this. I'll compute that. I'll just go ahead and grab that, and we go down to the bisection variant, and remember it said some Lambda function, so at least 2. So let's go ahead and create a Lambda function here. We'll go ahead and, what should we do? Well, I'll do this kind of funny function that I did before. So I think it was like x cubed minus, I can't remember what it was, minus 2, and then we'll subtract off like 2 times x. It was something like that. And I'll go ahead and just run that code here, and then I'm just going to, instead of compute bisection, it's compute false. And here, I'm just going to run it with the default in 10 iterations in these default tolerance parameters. And if I do that, this should give me the approximate root. The value. A and B, right? This is going to be a bit of a problem. Let me pick the right function. What was I doing before? I can't remember what it was. X cubed minus x minus 2x with that cosine. Okay, let me change that here. Minus x minus 2x. I think, let me run that. There we go. And about 0.467. Hey, and remember, is this working correctly? That's about what we saw before. The last time I was checking this. This wasn't from the previous video, the first video. So this is without interactivity. To do it with interactivity, this is where you could copy and paste again here, stuff I did above, where I showed some interactivity of just this computing. So I could say, let me go ahead and grab the interact function, just bring it down. There's a lot of copy and pasting, just some simple editing. And this would be, again, you gotta make sure to edit things correctly though. This should be compute false. This should be the Lambda function. Well, okay, actually, since I already defined f here, I could do it just like I have here. My a 0, let's say min 1. I think all of that looks fine. And so then within 10, when we're interacting with this, we're doing the outputs of this out. So right, this is the approximation of the root is this C. It goes A, B, C here. I think I also showed some interactivity right in the where I'm computing it. Well, I guess I didn't. I'm always just outputting all of the values. All right, never mind. So here you could just say like what happens is I increase n, right? And I'm not getting any improved value after, it looks like 7, 6, 4, 3, 2. There we go. 1, 2, 3, 4, 5. Okay, we're changing just a little at 5. You're pretty much done at that point. You're not changing the approximation after 6 or 7 iterations. In order to see that, you'd probably have to change that tolerance to, let's say, -7. Excuse me, I had to sneeze. And this tolerance maybe to -9. Just let's change some tolerances around. So if we at 5, it's just we're getting a really good approximation of the root. So we're not going to really improve after a certain time unless we really probably make these tolerances very small. But anyways, Here's without interactivity. Here's with interactivity. Here's one Lambda function. Change the Lambda function down below and copy and paste these two pieces of code below, and then perhaps change the A and the B values. And that's it. You'll have completed this part. And then this is to create a new function called plot false. So I'm not going to do that because I think you can carry on with finishing that. I want you to create a new function called plot false that's based on plot bisection, where you visualize the output of the false position method using widgets. If you want to get really fancy, then you can try to plot the last line used to approximate the root. This is not required. I'm not going to show it in the solution video. I think that's a really cool thing for you to try to figure out, though. And you could figure it out after you view the secant, how I do the secant method plots down below. And then I want you to visualize results with some Lambda functions with and without widgets. So if I go to plot false, and I say I want to create, or to create plot false, I want to base it on plot bisection. Let's go back up to plot bisection. And you could even do the improved plot bisection if you want. But you could also do, well, let's do that. Let's grab this one. Let's grab this code. And then let's go ahead and come down here. I want to create a new function called plot. It's already going to be improved, but we'll just call it plot false. Here's the big change. Compute false. That's it. That's all you have to do. So, all right. That completes that part of the activity. I'm not asking you to change a lot in this code. What do I need you to do? Change the algorithm it's calling from compute bisection to compute false. And then all you got to do to visualize the results with some Lambda functions is you could redo whatever, if you copy and pasted this code with the improved plot bisection, is just copy and paste these pieces of code that you did at the end of the previous activity that I talk about in the previous solution video. And instead of improved plot bisection, you're just going to do plot false. You're just going to change the name of this function right here that you're calling. That's it. I don't think you need to see me do that. So that's going to finish that activity. And then I ask you to compare bracketing methods. This is kind of like a summary activity, so I'm not going to provide the solutions for it. What you should really do is show some results. I would do it without the widgets, where you show some examples, potentially where one method outperforms the other in terms of providing good approximations of a root of a function sooner than the other one does. And you might just have to play around with functions to try to do this and see when does one algorithm outperform the other. I just want you to do a little research, spend 10, 15 minutes, examples where false position, does better than bisection, or Google or Bing or whatever your search engine that you like to use is. When does the bisection do better than false position, and why? And just try to understand a little bit about what the pros and cons of these different methods are. So that's going to be it for this video that really talks about the second activity and gives you some ideas about how to do this kind of more summary comparison activity. I would do it again without widgets, just create more code cells, show examples where each one does better than the other, and then just kind of explain why, when this happens. It takes a little bit of research. So I'm going to stop this video here, and then we'll go to iterative methods next. Thanks for listening.